So welcome to the 55th ASE seminar, Advanced Supercomputing Environment. My name is Kengo Takajima, so I'm leading the supercomputing regions of the Information Technology Center of the University of Tokyo. So before starting the seminar, so I'd like to briefly describe the history of the seminar. So it's 50-50. So initially, this seminar series of seminars studied by my former colleague, Professor Nakahiro Kanagiri, is now in Nagoya University. And this seminar is held irregularly when we have visitors to our center. And so sometimes we have other speakers from our center. So this time we have one speaker among my colleagues. The official language is not fixed. Today it's in English. And the first seminar was on March 3rd, 2008. So we accept any topic related to HPC and supercomputing. And the last meeting before COVID-19 was the 40th on February 4th in 2020. And during the COVID-19, we have one online meeting in February 2022. And we really started hybrid style from April 2023. So that's the 42nd. It's 2 years ago. And it's more than 10 seminars after that. So today, we are happy to host a very exciting seminar titled Machine Learning and Scientific Simulations, Theory and Applications. Our guest speaker is Dr. Vincent Liu. He is a postdoctoral researcher from the Department of Mathematics of the National Cheng Kung University, Taiwan. So we met 2 months ago in the conference in Tainan at the NC KU. It's a very nice campus and nice conference. So let me briefly introduce Dr. Liu. So he received his PhD degree in applied mathematics from the National Cheng Kung University in 2023. And he spent 1 year in the postdoctoral researcher in the Oden Institute of the Computer Science and Engineering at the University of Texas at Austin. His interest of research is a numerical fraction order differential equation, matrix decomposition, and the quantum information, and machine learning. So this is today's agenda. So first, we have a talk by Dr. Liu. And the next, my colleague, Professor Shimokabe, will talk about the more practical work in the machine learning applied numerical simulations. Actually, we have nearly 80 registrations from all over the world. So I think we have several participants from Europe and USA online. And I'd like to enjoy all of the participants for the next 90 minutes. Okay, so you can share your screen. Okay, so it's my great pleasure to introduce our guest speaker, Dr. Liu. And so title of his talk is Misidentification of Dynamical Systems Caused by Numerical Integrations. So please join me to welcome our guest speaker.
Okay. First of all, I would like to thank Professor Nakajima for inviting me to attending this workshop to share my recent research topic about how to assessing using the neural network to identify the dynamic system through some observation data. And before my talk, I would like to introduce one of the very famous conference that the International Linear Algebra Society, the ILAS, and this conference will be held in Kaohsiung from June 23rd to June 27th, and hope you can enjoy us for the conference next month. And so let me start my talk. Okay. So my talk is about the misidentification of dynamical system caused by numerical integration. And this work is joint work with Professor Richard Tsai from the Older Institute of the UT Austin, and which is my advisor during my first year of my postdoc research career. And then for introduction. So first of all, I would like to introduce you what is the dynamical discovery problem, or the how to identify the dynamics. So when we were in undergrad, we were taught about how to solve a differential equation, the autonomous differential equation. If we have some information about the function f, and we have the initial data. So that is the Cauchy problem. And we have learned a lot of methods to solve this, including the Laplace transform or using the power series method. And in numerical analysis, we've learned about how to use like the Runge-Kutta or the linear multi-step method to solve this kind of equation numerically. And what I'm going to do is to do the inverse problem. So the inverse problem is, if we have only the observation data from the trajectory, that means we only have some snapshots. And then we want to identify the function f, or the governing equation. So the key idea is, we don't know what is the function f, and we want to find what is it, what explicitly or what implicitly it is. So let me give you an example. So suppose that we have a pendulum dynamics. That means we have a ball that links to the ceiling with a very long string, and then we lift the ball to a certain height, and then we leave the ball, and we start to generate a dissipative trajectory. And you can see on the screen that the blue line, the two blue lines are the true trajectory, and the red dots are the sample data. And we sample these data with uniform time steps. So we have a fixed sampling frequency from the trajectory. So there are many methods that trying to identify the function f using the observation data. So these three regimes that aims to attack this problem. And the one is the sparse identification of nonlinear dynamics. They call the Cindy approach. So the Cindy approach is introduced by Burton and Kurz and their colleagues in 2016. And what they have done is they try to assume the function f reside in some function space, and these function spaces are given. So the problem is, if the function space is too large, and so that means we have a lot of candidates, for example, the polynomial. So we have a linear polynomial and quadratic, cubic, and so on, a higher order term. So that is only one-dimensional case. If we have two-dimensional, and that function space will be very, very, very big. So it scales poorly for large candidate libraries. So it requires a lot of CPU and RAMs. And so that is not a very good idea if you have only limited budget to try, and you're trying to do the identification problem. And the other one is called the Kuhlmann operator approach. So what Kuhlmann did before is that it embeds the state using some particular function, and they use this particular function to define some evolution. So in reality, the evolution of y, the true solution, is nonlinear. And then Kuhlmann trying to find they embed this state into a linear case, so that the operator kh is linear, so that they can transfer the nonlinear problem to a linear problem. And what is the most important thing is that the Kuhlmann operator, because this is linear, so we can find its spectrum and its eigenpairs. And we know from theoretic computation that the eigenpair satisfy this equation, so that if we have some information about the spectrum of the Kuban operator, then we can solve this function directly and to identify the function f. And this works has a lot of they use a lot of approach to implement the Kuban operator approach. For example, in NCOS in 2020, they proposed using neural network to identify the Kuban operator, and then they can try to backward understand what is the function f. And also, Cruz and Burton in 2018, they have some works about to connect the Kuban operator and the dynamic identification problems. And the other one is the neural network models. And this is the main target I'm trying to introduce you today. So very simple idea. They want to represent the unknown function with a given trainable neural network. So they want to train a neural network to fit the data we observed. So what they assume is that if the approximation they think that is good, that means we have the trajectory, that means the observation data is close enough to a numerical integration of the learned neural network. And this work is proposed by TQ Chen in 2018, and several analyses, including the Yakuji in 2024. He has done some analysis, and their analysis is quite similar to our analysis in my today's sharing. And we also our analysis is more delicate and more deep, including the nonlinear term and some what exactly is the misidentification means. So let me back to the neural ODE method, the neural network method, to identify the unknown function. So on the right hand side, you can see here that is the true trajectory or the true dynamics, and the right hand side is the using the. So we use a trainable neural network to represent the nonlinear function. And what neural ODE did is that they try to minimize, or they want to train the neural network here, such that the observation data is similar enough, is quite close enough to the numerical solution. Because we don't know how to solve this equation is very explicitly, very precisely. So what we only know is numerical method. So we only know numerical integration. So if we want to know how good or how well is the approximation be, we must to quantify the difference or the discrepancy between the true solution to the numerical solution. So they say if the true solution, if the numerical solution of the trainable neural network is similar to the observation data or the true trajectory of this unknown function, then we say, okay, the neural networks approximate very well. So the idea is they want to ensure the numeric solution is sufficiently close to observed data. That is the key idea of the neural ODE architecture. So let's take it back to the pendulum dynamics. So as you can see, I provide 3 figures, and in each figures there are red dots, black dots, and some curves. So the red dots are the sample data. So they are sampled within a different sampling frequency. So this is more fine. The sampling frequency is smaller than this one, because in this region we only have 1, 2, 3, 4, 5, 6, 7 samples. But in here we have more than 7 samples. It is obviously, and then we have the black dots, but it's not so so easy to see here. So as you can see here, here is a red dot and is a black dot. The black dot is the prediction. That means the fitting. So back to my previous page, the y of Tn is the observed data, that is the red dot. And on the right-hand side, that is the numerical solution, that is the fitting term, and that is the black dot. So these figures want to illustrate the difference between the red dot and the black dot. So in these three figures, we see that the fitting is very well. So every black dot, we can say they eventually overlaps with the red dots. That means we have no fitting error. But as you can see, we say that if the true trajectory is close enough to the approximation solution, then we say the neural network is a good approximation to the unknown function f. And we see from our experience that these red dots and the black dots overlap with each other, or they reside in a very small region. So can we say the approximation function, the neural network approximation function g theta is a good approximation to f? So this is a big question. And how do we know that the g theta is good enough? So we try to use more accurate numerical integration to directly integrate numerically the function g theta. So as you can see, these green lines are the true trajectory or the more high accurate solution to the dynamics learned by neural network. So in this guy, you can see before the time evolved to 10, the green curve or the learned dynamics is close enough to the true dynamics. But after time goes after 20 seconds, it deviates outside. Even though there is a phase error here, we can see the phases are different. And as you can see on the right-hand side, the trajectory learns tremendously bad, very, very, very worse. Because we see the true dynamics is a dissipative dynamics, so that the magnitude will tend to 0. However, the learned dynamics becomes expensive. It tries to explode. So can we say, even though the fitting error is very small, the learned neural network is a good approximation to the function f? The answer is no. So we want to answer the question, why gives this wrong? So I also show another example using the linear multi-step method. And as you can see, linear multi-step method is more robust to the stiff differential equation. And on the right-hand side, we have the fitting error that is very good. However, on the right-hand side, these two dynamics deviate outside. So even though using a more higher accurate or that is more robust to the stiff to the more stiff differential equation, the linear multi-step method can also learn very well. So our discussion is, neural ODE, even though it fits the training data very well for some certain edge, the higher accurate solution deviates from the true dynamics. So that is the conclusion of using the neural, the very short conclusion to the result of using neural ODE for nonlinear dynamic identification. And the other thing is, how about we try to learn another differential equation, then another dynamics. So the Volterra-Loca equation describes the population of two species, and the x-axis is the population of one species, and the y-axis is the population of another species. And this equation will the steady state of this equation will generate a limit cycle. So if we were trying to use the RK4 as our numerical integrator to learn these dynamics, we see probably it is a good approximation. And we have a very small approximation error, and we have a very good prediction, the prediction. That means the identification is very well. However, if we use the Ford Euler method, we can see even though the fitting is very accurate, but the true dynamics or the more higher accurate trajectory of the learned dynamics dissipated inside. It rotated inside. So what is the issue? Also, what caused these outcomes? So our question is, what caused the framework to learn an incorrect dynamics, even though we have a good fitting? So we try to answer this question by several aspects. So we suspect that, okay, maybe the numerical method influenced this defect, or the optimization process, the optimizer in the neural network training is not good enough, or that is caused by the rounding error. So we have a lot of effect. But today, I want to focus on numerical method. That means the stability of the numerical integrator. So before we go on, we need to make some assumption. We do not directly go into the discussion of the nonlinear case, but we first take a step back to the linear case. That means we assume that the true dynamics is a linear dynamics, and it is diagonalizable. And we also assume there is no training error. That means we can minimize the loss function to be very small. We can attain its global minimum or the local minimum. And then we also assume the learned dynamics is also linear, and it shares the eigenvectors with A. So that means in certain coordinate, these two dynamics can be regarded as the not the same dynamics, but in some certain sense we can directly analyze in the same dimension. And the other thing is we make further assumption that we fix our sampling rate. And then we assume the dynamics is dissipative or conservative. That means either the dynamics will rotate inside, or it will stay in the limit cycle. So for the pendulum dynamics, it is a dissipative dynamics because the amplitude decreased to 0. And for the the Vatera-Loca method, the dynamics, it generates a conservative dynamics. So that is a limit cycle. So we want to analyze these two terms, these two guys. And the third assumption is we analyze the one-step method and the multi-step method. So for the one-step method, we try to figure out how Fourier Euler, backward Euler, Runge-Kutta method will provide some insight, and also the trapezoidal method. And for the multi-step method, the Adam-Bashforth, Adam-Moulton, and the explicit trapezoidal method. So for the one-step method, because we have made some assumption that all the dynamics can be all the dynamic is diagonalizable, so we can directly look inside to the dynamics generated by its eigenvalue. So because we can directly read the test equation, so we can directly write down its the closed form of its numerical solution using like Fourier Euler, Runge-Kutta, or implicit trapezoidal method. So our optimization or our loss function can be directly rewritten as the following forms. So this guy is the observed data, and this guy is the numerical solution. So if we use the Fourier Euler method, then this guy will be this guy, the 1 plus lambda h with the power of n. And we have proved that there is always the minimizer is always exists and always satisfy this equation. So this equation says that the learned dynamics with using a given numerical integrator have some connection or some link to the true dynamics. So the lambda naught is the true dynamics, and the lambda hat is the learned dynamics. So from this equation, we can identify the location of the learned dynamics, while the true dynamics is known. Okay, so then let's go on. So for the qualitative analysis, because we know that the learned dynamics satisfies this equation, and we also assume that the real part of the lambda naught is either 0 or negative. That means the magnitude of this guy, the magnitude, the absolute value of this guy is less or equals to 1. So we can say that if the true dynamics is either dissipative or conservative, the learned dynamics will always reside inside the stability region of the selected numerical integrator. Because this guy characterizes the stability region of the numerical integrator. So for example, I plot the for Euler RK2, RK3, RK4, the stability region. So that means if we use the Euler method to learn the dynamics will always reside inside the blue circle. So this provides some information to identify where the learned dynamics will be. So for some case study, so for example, if we use the Euler method, that means the learned dynamics will reside inside the gray area because of the relation we found. So suppose the true dynamics is conservative. That means there is no real part. So the magnitude is equals to 1. That means the true trajectory, the learned dynamics lies on the boundary of the stability region. Because if we take the absolute value, that means the absolute value of P of Z equals to 1. That means the boundary of the stability region. So because we assume the true trajectory has no real part, but the learned dynamics resides on the boundary. That means that is totally on the left-hand side of the complex plane. That means there is the negative real part. So in this case, we are sure that no matter how small your sampling rate is, you will never get a conservative result using forward Euler method. How about backward Euler? Because we know that the implicit methods are more powerful and more stable because it has a more larger or more wider stability region. But similar to our discussion using the forward Euler, if the true dynamics is conservative, that means there's no real part on the lambda naught. The learned dynamics will on the boundary. That means it lies totally on the right-hand side of the complex plane. That means there is a positive real part on the learned dynamics. So that means every learned dynamics will generate an expansive trajectory outside the you can say the limit cycle or the steady cycle, infinity cycle, or any language you want. How about using a high order method? We know that high order method generates a more accurate solution to the true dynamics, right? But as you can see, the stability region of the RK2, the second order Raji-Kota method, looks like a capsule, and is totally stay on the left hand side of the complex plane. So also all the learned dynamics will contain a negative real part. So high order method may not be a good choice for dynamic learning problem when the true dynamics is conservative. However, if we use the implicit trapezoidal method, perfect. perfect. Why perfect? Because the boundary of the or the stability region of the implicit trapezoidal method covers the whole left-hand side of the complex plane, and the boundary is exactly the imaginary axis. So there is no real part. So if you want to learn the dynamics in a conservative manner, we can try to use the implicit trapezoidal method. Then we can always learn the dynamic with no negative or no real part. So our discussion is RK3 and backward-Euler method. One is a higher order method, and the other one is the implicit method. Can exhibit expensive trends to the learn dynamic to generate a dynamic that is expensive outside. As you can see here, there is a very small portion of the gray area extends to the right hand side of the complex. There's a very small area here. So if you look back to your numerical analysis textbook, and you can look very carefully inside the stability region, and you will see there is a very, very, very small region outside the imaginary axis. And also, this is also true for RK4. So what we have concluded, we summarize our observation is that every time you want to use a numerical integrator to learn a dynamics, you need very, very, very careful to look inside its stability region, because its stability region will provide some information of the structural issue of the learned dynamics. So if the true dynamics is conservative, then as I mentioned before, for Euler method, RK2, RK3, even RK3 or RK4 will generate a wrong dynamics, either dissipative or expansive. But for the implicit trapezoidal method, that will be super. It generates a conservative result. So that is the one of the take-home message. If you want to use a one-step method to learn a dynamics, you always need to focus on the select integrated stability region. The region matters. Okay, so we also have some discussion about the orientation, and this result is directly from the Shannon sampling theory, because we need to sample some data within the half of the frequency. So that is direct. So let us show some results. So if you want to learn a dynamics that is conservative, this dynamic will generate a circle with I think the frequency, the period will be 1/3, I suppose. Will be 1/3. And then if we use the Fourier-Euler method to learn this dynamics, the solid curves represent the learned dynamics. It rotates inside. So that fits our conclusion. Fourier-Euler method, because the stability region is on the left-hand side of the complex plane, so the learned dynamics rotate inside. And for the RK3, we say there is a very small region on the right-hand side of the complex plane. That means you will generate an expansive result. And if we try to learn this dynamics using RK3, we just zoom inside very, very, very close, very local to the starting point. We see there is a very small expansive trends here. And it also fits our conclusion. Using RK3 method will generate an expansive result. But if we're using the implicit trapezoidal method, the learned dynamics stay on the trajectory, on the closed trajectory. And we also have some numerical result using different numerical method for dissipative dynamic learning. So for Fourier-Euler method, it always generates the dissipative behavior. But for the RK3, because as I mentioned again and again and again, there is a very small part. There's very small area on the have the positive real part. So we found that using RK3 will generate expensive results. So that means if your dynamics have a very small dissipative effect, that means the absolute value of the real part of your dynamics is very small, then you shouldn't choose the RK3 method for your learning problem, because the stability region has a positive real part in this region. Yeah. And we also have some discussion on the noisy data. That means in the real world setting, we cannot have a very clear data without noise. So every time we have like the extrinsic noise, that means the noise is added on the trajectory, or the intrinsic, that means the noise followed by some Brownian motion, the noise from some Brownian motion. And in here, we only discuss the extrinsic. That means the noise is added on the trajectory. So I means I put a error, the error here. And so we define our loss function as this way, where the starting point is replaced by the noisy starting point. And we say that the minimizer, so this theorem looks a little bit complicated, but I can use one sentence to describe this theorem. The learned dynamics with the noise, with or without noise, is continuous of the noise. So that means the learned dynamics with noise is close to the learned dynamics without noise. And the difference is of the order of the noise, the first order of the noise. So that means if the noise is very small, then the learned dynamics with using the noisy data is close enough to, is sufficiently close to the dynamics without any noise. So that is what the theorem wants to describe. And on the right hand side, I show you some numerical experiments that the red curve is the fitted data, and the blue dots are the observed data. And I generate this training data using conservative dynamics. And that means all the data are stay on a closed loop, but I just give some perturbation on each point. And then I found that the learned dynamics generate an expensive result. So also we study about the linear multi-step methods. So just for some recall that the two-step add-on batch for method admits this formula, and the explicit trapezoidal method admits this formula. So we can also write down the minimizer of using the linear multi-step method for the dynamic learning problem. And so the minimizer lambda hat satisfy some certain equation, this equation. So because of that, we can also do some qualitative analysis to the conservative case. Why we state this conservative case? If you remember how we draw the stability region of the linear multi-step method, we use the boundary locus method. That means the stability region of the linear multi-step method is the complex number z, where the z satisfies the rho of z divided the small rho of z, the magnitude is less or equals to 1. And how we plot the stability region, we take the exponential inside and we characterize the locus of the stability region. And that is identically to what we have here. So that means the learned dynamics with a conservative case, the learned dynamics reside on the boundary of the stability region using the linear multi-step method. So for So we can also have the similar discussion as we have in the one-step method. If we're using the Adam Moulton method, Adam Bedford's method, we still need to pay attention to its stability region. So M2, Adam Moulton, Adam Bedford, the stability region do not lies on the imaginary axis, showing that either these two families of methods are not suitable for conservative dynamic learning, but we can find, but we know that the explicit trapezoidal method has the stability region on the imaginary axis. That means trapezoidal method is good for conservative dynamic learning. But the story goes very bad for dissipative case, because we cannot directly analyze the dissipative case. So we just show that if the dynamics is dissipative, that means it has, for example, it contains a negative, the real part is a -4, and you can see here the dynamics is a little bit chaos. So we cannot make sure that the learned dynamic will be conservative or dissipative, or it generates the same rotation direction as the true dynamic does. So for a brief summary, the true dynamics, if the true dynamics is conservative, then explicit trapezoidal method generate a conservative result. That means it can retain the structure of the dynamics. But if the true dynamic is dissipative, only explicit trapezoidal method can conditionally retain its dissipative behavior. So combining the two results from the one-step method and the linear multi-step method, we would suggest using the explicit or implicit trapezoidal method for dynamic learning problems. Why? Because its stability region covers or reside on the imaginary axis, or the right-hand or the left-hand side of the complex plane. So there are a lot of numerical integrators in real world. What we now have understood is that the stability region of the selected numerical integrator matters a lot and influence a lot to the structure of the learned dynamics. And here is some results. So for trapezoidal method, yes, it's still conservative, but for the other cases, the result is very, very bad. And for our dissipative case, you can see even I use Adam Moulton method, the third order Adam Moulton method, it generate an expensive result. Even worse for Adam Bedford methods. Also, we have some studies about the noisy data, and the conclusion remains the same. The learned dynamics is the learned dynamics is continuous with the noise level. Okay, so how about the accuracy improvement? Before my first part, I introduce you where the location is. But the second part is I want to introduce you how the accuracy is, how accurate it will be. So we need to back to for the one-step method, we need to back to understand the relation between the learned dynamics and the true dynamics. So by using the Taylor expansion, we can find that the learned dynamics, if we use for Euler method, the accuracy of or the consistency of the dynamic learning problem is of order h. And if we're using the implicit trapezoidal method, it is the second order accuracy. So the question is, because we say that the Fourier-Euler method and the implicit trapezoidal, the Fourier-Euler method is not a good choice because it generates a wrong wrong structure. Can we correct it? Or because implicit trapezoidal method is only second order, can we use this method to fourth order, high order? The answer is yes. Why? And how do we accomplish this? The retraction interpolation. We can use retraction interpolation to lift the accuracy from second order to the fourth order in the implicit trapezoidal method, and we can also lift the accuracy of the fourth order method to the second order. But if we want to use the retraction interpolation, we must be careful that we do not destroy the structural issue. That means if it is dissipative, we must retain its dissipative behavior. If it is expansive, then we must retain its expansive behavior. So we have some result that if we find that the real part of the learned dynamic using for Euler has some certain relation, then we can use the retraction extrapolation to correct the trends or the amplitude error, and then we can also have a higher order accuracy. And we can also do the same tricks to the trapezoidal methods. So I summarize using these two tables. If the true dynamics is conservative, then either using implicit trapezoidal method or explicit trapezoidal method and the retraction extrapolation, it can always preserve the conservative behavior, and then we can lift the accuracy to a higher order accuracy. But for the true dynamic is dissipative, then we must be very, very, very careful of the non-real part. Otherwise, we will extrapolate an expensive dynamics. So to finish my talk today, I want to conclude my talk using some understanding using the numerical integrator to learn a nonlinear dynamic problem. So if we consider back to the pendulum dynamics or the Volterra-Loca equation, if we use the four-Euler method, the RK2 method, we found that some of the equation will provide a wrong trends. That means, as you can see, if you remember what I have shown in my second or third page of my talk, if we use a fourth order four-Euler method for the pendulum dynamics, it sometimes generates an expansive result or an dissipative result, and it had a very strong dissipative behavior or properties. And if you still remember, I showed the result using the four-Euler to learn the limit cycle in the Volterra-Loca dynamics. It rotates inside. So we want to base on our understanding using the linear dynamic to answer this phenomenon in nonlinear dynamics. So what we have finished is we try to using the linearization method. And so suppose that if we have a trajectory given given a step size, and suppose that we use four points, the current state, next state, and the 3H and the 4H. We're using these four points to define a constant m. That means the sample. So that means that these 2 points. That means these 2 points, the points of the sample points on the trajectory have a fixed distance. It do not be so that means that the dynamics will not be explored dynamics. Then we find that this m provides a bound for the dynamic learning problem. So G is the learned dynamics. the learned nonlinear dynamics. And dg is the derivative of the dynamics. So that means the spectrum is bounded by M, but has some very small perturbation of the sampling rate. So if we back to the linear, so if we back to a linear problem, M is equals to 1. Then and dg is a lambda. So that means it is 1 plus h times lambda. That is for all the case. And these two aligns together. For the RK2, we have the similar result. So these three guys, if we consider the linear part, these three guys are 1 plus h times lambda hat, and this guy is 2 h squared over 2 times lambda hat squared. And these guys are 0. So that means the bound M bounded the spectrum of these guys. And if we back to the linear case, we find, okay, that is also equivalent to what we have discovered in the linear dynamic learning problem. Also, we have some similar result for the implicit trapezoidal methods. And for conclusion, and this call, we provide some analysis using one-step method and linear multi-step method. And we say that the implicit trapezoidal method is the best because the region of the stability with the within the selected numerical integrator matters a lot to what we will get for the dynamic learning problem. So a very important take-home message is be aware of the shape of the stability region. The stability region will provide many information to your what you will get after learning. And we also show that using regression extrapolation can enhance accuracy without using extra data. Also, we showed that the noisy case and the learned dynamic is continuous to the noise level. Okay, so thank you for your attention, and this is my personal information. And on the right-hand side is the web page to the ILOS conference. And thank you so much for your attention. Thank you so much.
Okay, thank you very much.
Thank you so much.
Our second speaker is my colleague, Professor Takashi Shimokabe. Title of his talk is a fast prediction method for steady flow simulations over multiple domains. So please join me. Welcome.
Thank you very much. And I'm Takashi Shimokabe from the University of Tokyo, and I'm talking about the fast prediction method for the steady flow simulation over multiple domains. That is very more practical the aspect of the machine learning. Okay, so what about the computational fluid dynamics? The CFD is an important application in the field of HPC. And since the CFD application are based on many computational grid measured particles, so it is well known that the computational cost of the CFD is relatively high, and the CFD application, required a lot of the computational time. So recently, the CFD has been used in the variety of the field, not just the example on the previous slide. The CFD simulation are also used in the steady flow simulation. That means that do not change with time, and such as blood flow simulations. So, however, even if it is the steady flow simulation, since the CFD requires large computational resources, it is indispensable to accelerate the process of the CFD analysis. In order to solve this problem, so we will use the deep learning to build a fast surrogate for the approximating the steady flow simulations. So here is a challenge, and then we are developing the deep learning surrogate for the 2D steady flow. the training method, training model on the multiple GPUs. And also we are predicting the flow around the complex shape. And also we are developing the prediction method and using deep learning with the boundary exchange for the steady flow simulation with the varying the size of the computational domains. And here is a basic idea of the deep neural network DNN prediction of the flow. So first we perform the CFD simulation in a traditional way to generate the training data set. In our research, we use the Lattice-Boltzmann method for these simulations. And once that we have the data set, so that we build a neural network architecture based on the convolutional neural network, CNNs, and we train it. And after training, so we can use the trained neural network to predict the CFD simulation results, which means that the CNN may become the fastest simulator. So in our research, and we use the Lattice-Boltzmann method to generate the our training data set. And in this method, so instead of the solving of the Navier-Stokes equations directly, so fluid density on a lattice is simulated with streaming and collision processes. Since distinct particle motion can be decomposed over many processors, so efficient implementation on the parallel computers are relatively easy. So, however, the LLVM still require many iterations to converge the value or to achieve the desired result. And so here is the data set that we use for the training the CNNs. So in order to make the training data set, so we perform the Lattice-Boltzmann method simulation using the D2Q9 model with the Reynolds number of the 20, and that which is relatively small number because we are simulated for the steady flow simulation. So the fluid flows along the x-axis are here, and we place the random sized cylinders or the polygons at the random locations. So since it is difficult to train the model using the large size data, so we clip the data with a size of the 256 times 128 from the original data, and we split about 60,000 data into the training data set and the validation data set. And in this case, so we use a signed distance function to represent the geometry in such as the cylinders and the polygons. So SDF provides the universal representation for the different geometric shapes and works efficiently with the neural networks. And SDF provides the zero at the object surface and the positive distance in the fluid and the negative distance inside of the object. And SDF is very, very often used to represent the geometry in the conventional the fluid dynamics simulations as well. And here is the neural network architectures we used. The encoding part and here is shared by all dimensions, in this case x and y, and the decoding part is different in each dimension. So the encoding part consists of several convolution layers, and the decoding part consists of several deconvolution layers. And we use the signed distance function and the boundary condition of the velocity as input. And the signed distance function is to use the represent the geometry as I described. So this model provides the velocity field as output. So in order to improve the accuracy, the model provides the information of the location object as a mask. So here is a prediction result for the single domain case. The left side of the figure, here, the CNN prediction and of the velocity field. And the middle figure shows the LBM, the ground truth. And the right side of the figure, the difference between the CNN prediction and the LBM result. As shown in the figure, our model will predict the LBM ground truth. Okay. And as I mentioned, the training itself is done by placing the simple shapes such as the cylinder and the polygons. So here we show the result of the prediction and the complex shapes that are not in the training data set. On the left is the prediction by the CNN, and similar to the previous slide. In the middle is a ground truth of the LBM simulation, and on the right side is the error between the two of them. So we can see the CNN predict the result with a sufficient accuracy for the geometry that do not exist in the training data set. And the prediction time but the prediction time is very, very fast. The LBM simulation takes the 41.4 seconds for this case, even with GPU computation, while the CNN predicts the result just only the 0.6 seconds. So the CNN predicted has achieved high accuracy with the significant reduction in the computational time. Okay. And then now, we will the next to the multiple domain case. So in order to predict the result of the large size domain and the flexibly handle the input data of the various sizes. So we propose the prediction method using a CNN with the boundary exchange. So in this method, we train the neural network model to predict the single domain result and apply it to the decomposed subdomains to predict the simulation result in each subdomain. In order to maintain the consistency between the value in the subdomains, the boundary exchange between the neighbor subdomain is performed. And here is the detailed explanation of the performing the CNN and the boundary exchange. The CNN, CNN that predicts the value in each subdomain using the boundary value as input. After that, the updated boundary value are transferred to the neighbor subdomain, and the CNN and the boundary exchange are performed iteratively until the value converge. So, for example, this is in the first step, the blue region is predicted by using the CNN, and after that, the boundary, the data on the boundary region is transferred to the neighbor subdomain. In this case, the green region, and after that, the CNN predicts the value on the green region, and repeat this process, and the end to obtain the final result. Okay. And here is the prediction result for the decomposed multiple domains in this is 3 subdomains case. So left side of the figure, the initial prediction by CNN with the initial unknown boundary condition. After the CNN and the boundary exchange between the subdomains performed iteratively, and the prediction value are converged to reach the final prediction. And this is the final prediction result. And the right side of the figure here is the LVM's ground truth. So as shown in the figure, there is a little difference, but the developed method can accurately predict the value in almost all computational domains. And here is the here is the detail of the convergence of the prediction with convergence of the prediction result. And this graph shows that the changing of the velocity in the x direction along the y-axis. This is a cross section. So you can see that the value are approaching the correct ones affected by the updating by the boundary value of the each neighbor subdomain. So that is the time step loop, the iteration that the 300. So maybe the repeat again this movie, I think. So yeah, this is the initial value, and after that, the updating each subdomain, and the value is converged. Okay. So here is the prediction. Here is the prediction result for the decomposed multiple domains with a complex shape that are not in the training data set again. So the left side of the figure, this one is an initial prediction by the CNN with an initial unknown boundary condition. And after the CNN and the boundary exchange between the subdomain are performed repeatedly, so prediction value converged to reach the final prediction that here. And the right side of the figure, this one is the LBM, the ground truth, obtained by the LBM simulations. And also that is the error between the CNN and the LBM. So that's shown in the figures. Also, of course, there is a little difference, especially in the boundary region. But the prediction value are converged to reach the final prediction. Here. Okay. And so the next is I will introduce some of the most recent result from the joint research. So in this study, we have improved our original prediction method and apply it to the prediction of the blood flow simulation. So here is the simulation result for the simulation result of the blood flow. And the red and the black boxes in this figure represent the subdomains. So in this study, we propose a new model that called the hard constrained CNN surrogate model. So which is based on the original proposed method. So the prediction of the blood flow means the prediction of the result of the simulation in a blood vessel. So that is the simulation has words, not to the periodic boundary. So we set the boundary velocity value as 0, And also the output is very different from the original one. The mass conservation is especially important in the blood flow simulation, so that the mean flow rate is utilized in the new surrogate model, and this rate is satisfied at the output of each subdomain. And here is the prediction result. Good. Here is the prediction result of the blood flow simulations case. By adding the constraints, the simulation result are predicted with the good accuracy, and also by using the mean flow rate, the number of the iterations required to converge is also reduced. In the simulation, in this simulation, the FEM, the finite element method, was used to create the training data set, not the LBM. So we have found that the proposed method can be used to predict the result of the simulation other than the LBM. And finally, I will show the difference in the prediction accuracy between the original data-driven method and the hard constraint method. And please see this table. And here is the global relativity error between the CNN and the FEM, the ground truth, over the entire computational domain. So it can be seen that the new method, which is used satisfying the mean flow rate, is more accurate in its prediction. So this is it's small, but this is the top panel is the new model, the accuracy result. Okay. So here is the conclusion of my talk. So we have the deep learning, the fast prediction method for the steady flow simulation. So prediction, the LBM, the lattice Boltzmann method result by using the convolution neural network CNN, and predicting the simulation result on the large size domain using the CNN with the boundary exchange. Then there's a new model with the hard constraints on the original proposed method is proposed and recently, and it can predict the blood flow simulations with good accuracy. And this new model is we consider the mass conservation. And the future work is we will extend this method for the 3D simulation case, and also we are considering adding other constraints. So thank you very much for your attention.
Okay, thank you very much. Okay, so thank you very much for joining for this Friday evening, early evening. So thank you very much for coming. So I'd like to close this seminar today. And the next seminar will be 2 weeks from now. And it's also related to the integration of the machine learning and simulation. And if you are interested in, so please join us again. So thank you very much. So have a nice weekend.